Okay, so now we're going to talk about heat and heat transfer. So this is going to get a bit more, not necessarily complex, but definitely going to build on everything that we've learned so far. So our learning targets, I can define the difference between heat and temperature, and that's actually really challenging for some people who haven't taken thermodynamics courses or chemistry courses before. A lot of people will say that heat and temperature are extremely interchangeable, and we'll talk about that. I could define thermal equilibrium. You guys have heard the word equilibrium a million times. I'm sure that you already could define that, but we'll talk about what it actually looks like. I could describe the two types of thermal expansion. Those types of thermal expansion aren't really tested anymore, but I think they're pretty interesting, and that's why I talk about them, because there's a lot of actual life examples that we can talk about with them. I can identify the three temperature scales. You all took Earth Science many moons ago, so hopefully you at least have the three temperature scales known from that, that they are Fahrenheit, Celsius, and Kelvin. I can explain the zeroth law of thermodynamics, which is always a law that's kind of like, well, duh, sure, that works. So hopefully that one's not too challenging. And then I could describe the three types of heat transfer both qualitatively and quantitatively. And again, those of you who took Earth Science probably can already tell me the three types of heat transfer, but I am also very aware that that was about 4 or 5 years ago at this point. So, once again, in everyday language, a lot of us use the terms temperature and heat really interchangeably. Like, oh, the temperature is so high outside, it's so hot outside, whatever people say. So, in physics, those two words, however, are going to have really different meanings. So, if you think about a couple of different scenarios, when you touch a piece of metal versus a piece of wood resting in front of you, which one is going to feel warmer? And you could say the same thing if you were to heat them both up, which one is going to feel warmer as a result of that? Another question that you can consider: when do you feel warmer? When the air around you is 90 degrees Fahrenheit and dry, or when it's 90 degrees Fahrenheit and it's extremely humid out? Um, so in both these cases, the temperature of what you're feeling is the same. So why is there actually a difference? So temperature definitions include some of the following. So there's a measure of warmth or coldness of an object or substance with reference to some standard value. Uh, so a big reference point that we use sometimes is room temperature. Is it warmer or colder than room temperature? And we'll talk about the idea of room temperature. I'll make sure that I bring it up when we talk about thermal equilibrium. Another definition of temperature would be any of various standardized numerical measures of this ability, such as the Kelvin, Fahrenheit, or Celsius scale. So anything that can be measured on those three scales would be considered temperature. A measure of the ability of a substance, or more generally of any physical system, to transfer heat to another physical system. So we're saying it is the ability to transfer heat. That's what temperature is. And that's kind of important to think about as well, because that's straight up saying that temperature is not heat. It is the measure of the ability to actually transfer heat. Okay. And then the last one is a measure of the average kinetic energy of the particles in a sample of matter expressed in terms of units or degrees designated on a standard scale. So once again, we know that the average kinetic energy of particles in some kind of gas or matter, those we can say is directly related to temperature. We've talked about that a few times at this point. So, in order to actually measure the temperature of the substance, we're going to need a thermometer. Typically, more often than not, we use the thermometer. If you have something else that measures temperature, that's really cool. I would love to see it, if it's safe. So, a measuring device known as a thermometer that visibly changes and is calibrated to a scale. So, whether that scale be Celsius or in Fahrenheit on either side. Thermometers are going to relate the change in a physical property of a substance to its temperature. So what happens is the thermometer looks for some kind of change in volume of a gas or liquid, the change in the length of a metal strip or wire, or the light or infrared radiation that's actually emitted by an object. And then, or another way, if we're not going to directly measure the temperature with a thermometer, what you want to do, or I'm sorry, in order to, if you are not, like, let's say it's a liquid or something like that, you can obviously just put the thermometer straight in the liquid. But if we have something that is not like that, what we would want to do is have the thermometer come into contact with whatever substance it is. So when the thermometer has actually settled on a value, we say that the thermometer and the substance are in thermal equilibrium. So if you've ever had a fever, when you put your the thermometer underneath your tongue, you're bringing the thermometer in contact with whatever your temperature of your body is, and you know that it takes a couple of seconds. You can't just put it in your mouth and say, okay, yes, this is the reading. You have to sit there and wait until it actually beeps, until it's fully sure that you're in a state of thermal equilibrium. Thermal equilibrium, as we probably understand, is two objects or substances being at the same temperature. Okay. Just some pictures of various types of thermometers. A gas thermometer, we're going to have a manometer, which measures the pressure. And this is how we actually measure the temperature of a gas, just by seeing how much the pressure increases, because once again, we know that pressure and temperature are linearly related. So thermal expansion. So most materials expand when their temperature increases. So if you think about, if you all drive, so in the summer, your tires actually not necessarily inflate as it gets warmer, but you could definitely see the pressure in your tires going up when the weather is warmer, as opposed to when you first get in your car in the morning after it's been cold all night, you could definitely see a decrease in pressure because of that decrease in temperature. Another really good example is if you think about a tight metal jar. If you run it under hot water, that lid is going to much more easily be able to come off. And I can't count how many times that's happened to me, but hopefully a relatable situation. Okay, so both that liquids expanding in a thermometer when you actually take the temperature, that is another example of seeing a temperature increase by method of thermal expansion. So we'll talk about two types of thermal expansion. Once again, these are not heavily tested anymore. So I would not be too worried about them, but like I said, I think they're kind of interesting to learn about because there's a lot of actual applicable examples. So suppose a rod composed of some substance has initial length L naught at initial temperature of T naught. If the temperature is changed by delta T, the length is going to change by delta L. So that delta L, we have an equation for. So delta L is going to be equal to alpha L naught delta T, where alpha is the coefficient of linear expansion. So if I have some metal bar here, for example, whether or not it's a metal bar, it doesn't really matter. As long as when I heat it, it expands. So I have some metal bar, let's say, and it's at some initial temperature, and then I raise that temperature. So it's really that I'm increasing, not just changing. I'm increasing the temperature. In the case of expansion, if I was talking about contraction, I would be decreasing the temperature. But if I increase the temperature, then the length of this metal rod is going to increase by some new factor, delta L, which is calculable through this equation. And now the new length is L here. So the initial length plus this change in length. The length itself, the new length, is not delta L. That's important to note here. It's this. You have to add it to the original value. Okay. The other kind of expansion that we could talk about is if we think about it in terms of volume, and substance has initial volume V naught at an initial temperature of T naught. So if the temperature gets changed, once again increased in the case of expansion, The volume is also going to increase by a factor of delta V. And if delta T, as long as it is not too large, delta V is going to be directly proportional to delta T. Once those temperature values get too large, it's very hard to actually draw this direct relationship between volume and temperature. So that's just kind of the point that they're making there, and we'll see that a little bit as we talk about this some. So the change in volume, and once again, they really don't test on this that much. I just think that it's interesting, and I may as well teach you some more Greek letters anytime that I can, right? So the change in volume, delta V, is going to be equal to beta V naught delta T, where beta is the coefficient of volumetric expansion or volume expansion. Okay. So, or an example that this is extremely important in. So, if water gets heated above 4 degrees Celsius, it expands. So, if in the temperature range from 0 to 4 degrees Celsius, water's volume actually decreases as temperature increases. So, when I said before about a change in temperature, you can clearly see that volume versus temperature here, this is not a consistent relationship as far as direct proportionality. Between 0 and 4 degrees, you can actually see a completely inverse relationship. Okay? So with that in mind, 4 degrees Celsius water is actually more dense than 0 degrees Celsius water, so therefore water must have its greatest density at 4 degrees Celsius. So again, they don't really test on this, but I think this is really interesting because this is what's going to protect any kind of life in bodies of fresh water, since the water on the bottom, at the very worst, is going to be 4 degrees Celsius, which we know is not quite freezing. 0 degrees Celsius is freezing. So that's I think pretty fascinating. So the 4 degree Celsius water, because it's a greater density, that's what sinks to the bottom of the lake. So the ice that forms at the top, the 0 degrees Celsius water that's actually floating up there. So anything that's down here is extremely protected. So we will move on to things that are actually more relevant, but sorry for the diversion, but I did think it was worth mentioning. So 3 common scales are going to be Fahrenheit, which we really unfortunately use in the US. Celsius is what most of the world uses, and then Kelvin is what we use in physical sciences. It is known as the absolute temperature scale. 0 degrees Kelvin is the coldest temperature that there can be. There cannot be a negative Kelvin value, so if you get a negative temperature, you probably did. If you get a negative temperature in Kelvin, you definitely did something wrong and you need to go look at it. So as we talked about on the first day of these notes, in order to convert from Celsius to Kelvin, you just add 273. And notice here that it's Kelvin, not degrees Kelvin. I don't know if they'll take points off for that, but it drives me insane when people write degrees Kelvin. I don't even really know why that's the case, but I just know it drives me nuts. So, and once again, in physics, we generally use Kelvin, and so when we did that example the other day, if the temperature of a gas, let's say, goes from 30 to 60 degrees, you can't use PV equals nRT and say that temperature doubles, because PV equals nRT uses the Kelvin scale because R is joules per mole Kelvin. Okay, so in Kelvin, that gas only went from 303 Kelvin to 333 Kelvin, which, yes, that's an increase, but it's most certainly not double like what's represented in our Celsius scale. So if you think about it, when you pour hot water into a cold cup, the water cools down the cup and the cup warms up as they approach thermal equilibrium. So if you think about, I get a drink with ice in it, it's going to make the drink colder, right? So the reason for that temperature change is that energy is going to flow from the higher temperature to the lower temperature object. And that flow of energy is what's called heat. It will always go from hot to cold, never the other way around. So if you think about if you were to hold an ice cube in your hand, that ice cube melts as a result of heat transferring to your hand, not the cold transferring to your hand. Okay? Um, so on the AP exam, your reference table, Q is the symbol for heat. Heat is also known as thermal energy transfer. That's also very important. I told you before that temperature is the ability of heat energy to be transferred. So heat being thermal energy transfer hopefully makes sense. So this kind of summarizes our idea of heat and temperature being different. So temperature is a quantitative measure of an object's hotness or coldness, whereas heat is the energy that's physically moved from one object to another because of a temperature difference. And those are going to be really important to remember, at least in terms of when you have to explain things qualitatively, because if you trip up on the words, the differences between heat and temperature, you are going to have a bad time. So because heat is a form of energy, the SI unit, as we know for energy, is the joule. So I will write that here. Remember that that is simply J. Hopefully we all remember that. Okay. So the zeroth law of thermodynamics, and again, this one was always silly to me when I learned about it in chemistry, because it was kind of like a isn't this obvious thing, but maybe it's not. So two objects are placed in thermal contact with each other will eventually become the same temperature, and when they do, we say that they are in thermal equilibrium. So the zeroth law of thermodynamics says that if two objects are in equilibrium with a third object, that must mean that they're in equilibrium with each other. So what this is basically saying is that if T1 is equal to T2 and T2 is equal to T3, then T1 must be equal to T2. And I think my mouse here didn't do that right. Meaning I didn't do that right. So if T1 is equal to T3, because those are in contact with each other, and T3 is equal to T2 because those are in contact with each other, then T1 and T2 must be equal to each other, even though they are clearly not in physical contact with each other, but because all three are, hopefully it makes sense why they would be in thermal equilibrium with each other. Okay, so if we think about this in terms of conservation of energy, so when two objects are isolated from their surroundings and then they're brought into contact with one another, once again, we know that heat is going to flow from the hotter object to the colder object until those objects actually reach thermal equilibrium. And because there is nowhere else for the heat to actually go, and because energy is conserved, I'm going to write this down, that the heat that is lost from the hotter object plus the heat gained by the colder object is equal to 0. Okay, so if energy is conserved, that means that whatever heat is lost from the hotter object to the colder object, those heats have to be equal to each other, as long as there is no external work done, and we'll talk about that eventually. So any heat that is lost from the hotter object has to be equal to the heat that is gained by the colder object, because that is how energy conservation and thermal equilibrium works. So there are three mechanisms of heat transfer, and once again, you might remember these from earth science, but we're going to talk about them in the context of physics. The one that's going to be really important that we talk about is conduction. Radiation is, I would say, well beyond the scope of this course. Radiation is extremely complicated. We'll talk about it a little bit, but you won't need to worry about it too much. So conduction, convection, and radiation are the three that we are going to talk about. So conduction is the flow of heat due to the transfer of kinetic energy due to molecular collisions. So what that's basically saying, two things are in physical contact with each other. So an example of conduction, once again, back to holding an ice cube in your hand, I am in physical contact with that ice cube, so I am conducting heat from my hand to the ice cube. Okay. So in the diagram here, the kinetic energy red gas molecules, they have a higher kinetic energy and they're bouncing off the walls in their container. When they hit the wall of the divider there between the red and the cold, or I'm sorry, the red and the blue, which represent hot and cold respectively, they're going to transfer some of their kinetic energy to the cooler, slower, and lower kinetic energy blue gas molecules. So, as you remember from kinetic theory, we treat these collisions as elastic, so there is no loss in kinetic energy. Some of it just gets transferred from the red molecule to the blue molecule. And that's now a really important statement here about those collisions being elastic as far as energy conservation goes, because this becomes much more of a headache if energy is not conserved. Okay, so over time and over many, many collisions, the red and blue areas eventually come to a thermal equilibrium, in which they are going to share the same temperature. So the red molecules have lost energy and the blue molecules have gained energy until they now, on average, have the same kinetic energy. So both areas have reached the thermal equilibrium because of conduction, once again, conduction being the transfer of heat due to physical contact. Okay. So another example of this, if you think about the hot coffee molecules in this cup, they bounce against the ceramic walls of the mug, which gives kinetic energy to the cup with the molecules that are in the cup wall itself. So when you pour hot coffee into a mug, that mug usually isn't warm. It becomes warm as a result of these collisions and the hot coffee molecules bouncing against the walls of the mug. Okay. I'm gonna click this simulation in a second here. So we're gonna talk a little bit about the rate of heat transfer and how many things that's actually going to depend on. So you can modify the temperatures of the gases. You can talk about a lot of the different factors here. We'll click it. And so what it says here in this lab, you're going to examine the factors that affect the rate of heat transfer through a barrier that is separating two gases. And clicking on any of the parameters below will cycle your experiment through all the possible values for the parameter. We're going to click begin here. So what we can do is we could say, okay, my current material is brass that is separating these two. And clearly we could figure out the volume of it if we wanted to, but you could see that on the left side currently, the temperature of the krypton molecules is about 270, whereas the temperature of the argon on the right side is about 260. And you can see that the rate of heat transfer here is 90 kilojoules per second. So if I start clicking things here, and if I, let's say, up the temperature, if I up the temperature, you can clearly see that heat is now transferring from the hotter krypton to the cooler krypton. Let's see, if I increase the amount of molecules, I'm going to obviously continue to do that. What would really happen is that this temperature should also be getting greater as I do that, or if I increase the temperature, they should be moving faster. Okay. I can change the material of how good of a conductor of heat this is between bronze or gold or lead, right? So your rate of heat transfer is going to change depending on what you actually have here. So silver, for example, clearly going to be able to have a very high rate of heat transfer, which hopefully makes sense when you think about how fast silver heats up. Okay, same for copper. Aluminum is also pretty high. Okay, so, and brass is also a pretty good one. It's not as good as the others in terms of being able to conduct the heat through, but definitely silver for sure. So I mean, you can look at different gases as well. If I increase the temperature of these, now you notice if they're at the same temperature, there's going to be no rate of heat transfer because they're in thermal equilibrium. Okay. If I raise the temperature once again, if I am changing the bounds of my barrier here, you can clearly see that all of that is going to affect the rate of heat transfer, and hopefully that makes some sense. Okay. So, if I come back to my PowerPoint here, I always call it a PowerPoint even though it's just a Google slide. What we're going to talk about now, so we're looking at the rate of heat transfer. So it's going to depend on all of these things. So it depends directly on the relative temperature at both ends, T2 minus T1. And so this is a similar apparatus of what was being shown in the simulation there. If there's no temperature difference, there's not going to be any heat transfer. Okay, if two objects are in thermal equilibrium, there is no reason for there to be any heat transfer. If I put my hands together after they've been sitting there for in room temperature, there's not going to be any heat transfer, okay? But if I put one of my hands on a cold surface for 5 minutes and then I touch my other hand, then there will be heat transfer from my warmer hand to my colder hand. But in general, my hands are the same temperature. So there's no heat transfer if I touch them together. It's also going to depend directly on the cross-sectional area available for collisions to occur. So depending on how much area is actually available, that will be able to increase the rate at which heat can transfer, because that means that these molecules have more space to collide, more space to actually transfer heat. It is inversely proportional to length along which the heat must pass. So the longer that you actually make this tube here, the harder it is for the molecules to be able to conduct to other molecules, obviously because they're separated by a greater distance. And then it is going to depend directly on the conductivity of the materials. The conductivity of the material, example, silver is extremely good at conducting heat. So silver, for example, has a higher conductivity than lead. Okay, so mathematically, we can write an equation for this, and this is going to be an important one to know. I think it's on your reference table. I'll have to double check that. I hope it is. So this is the rate of heat transfer. Remember Q over delta T, just in case. I don't think I pointed that out before. Sorry, I definitely should have. Okay. So once again, directly proportional to conductivity, directly proportional to the cross-sectional area available for the collisions to occur, and directly proportional to the relative temperature at both ends. So whatever T2 minus T1 is, under the assumption that T2 is the hotter temperature. Okay, and then it's obviously, if T1 were greater, do T1 minus T2, or you could just take an absolute value. It doesn't really matter. So hopefully that makes sense. So if I continue to think about conduction, I could say both blue blocks are cold and at the same temperature, and then both red blocks are hot and they are also at the same temperature. And so my question is, which set of blocks is going to reach thermal equilibrium first? So hopefully you can look at this relatively quickly and say, okay, B is going to reach thermal equilibrium first because there is a greater area here, greater cross-sectional area for collisions to occur, as opposed to in A here, there is only this because block B is, the blue block in A is smaller than the blue block in B. So there is more area here for collisions to occur, and therefore thermal equilibrium will be reached faster. So the next one that we will talk about is convection. Convection is the process by which heat is transferred through the mass movement of molecules and gases and liquids from one place to another. So when you learned about weather, hopefully you learned about whether things that are warmer, those rise, things that are cold, they're denser, they sink. So that mechanism is not only important for some of these examples as far as the weather that we get here. So you have warm masses moving up, cold air masses moving and sinking down. Hopefully you've all boiled a pot of water before as well. So all of that bubbling that you get is a result of convection in liquids. Okay. So a lot of convection is also really important in astrophysics. So all stars have a convective layer, and that is how heat is actually transferred. Right? Stars aren't sitting there touching each other and gaining more heat. That'd be really bad. Anyway, but that's so they all have some kind of convection zone. Depending on how large that convection zone is, that's going to depend on the current state of life of the star, as well as how large that is, the life of the star, what elements that it's fusing at a particular time. Okay. So once again, convection and radiation we're going to talk very little about. It's really conduction that we're going to heavily focus on. So radiation is going to be energy transfer by electromagnetic waves. So you feel um, radiation as a result of our very lovely average star in the sky, that being the sun. That warms you when you sit directly under, or if it's directly overhead and you're sitting outside and it's a warm day, you can feel the sun warming you. Or if you've ever been in front of a campfire and close to it, you can feel that warmth is getting next to you. Okay. When we talk about electromagnetic waves, we will talk a lot more about radiation. So radiation includes anything that you would see on an electromagnetic spectrum, whether it be radio waves, microwaves, visible light, not just the infrared radiation that you feel from the sun, okay? And radiation is cool in that it does not need a medium in order to transfer heat. It can travel through a vacuum, okay? As we know, light can travel through a vacuum. It does not need any kind of ether or matter to bounce off of. Okay. Just a cool side note, if any of you ever decide that you're going to take an astronomy class or something like that, I think that it's kind of cool to think about radiation of a star. And stars, again, obviously, are going to be our biggest culprits of radiation. So what this looks like is the rate of heat transfer of a star. It looks like this, and you can see that it's extremely dependent on temperature. Um, Once again, this is not going to be on your AP exam, but E is some number between 0 and 1. The darker the surface, the greater the heat transfer is going to be, because darker surfaces absorb heat better. The opposite of emissivity would be albedo, if you ever learned about albedo. A measurement of like how well something reflects light. Sigma is just a Stefan Boltzmann constant. It's like 5.67 times 10 to negative 4 watts per meter Kelvin. I'm probably making that number. I'm making that number up, but I know that those might be the right units. But it's just a constant. Boltzmann did a lot of work with heat transfer, clearly. And then A is the surface area of the object. So if we're looking at the sun, the surface area of the sun would be 4 pi r squared. So hopefully this is kind of interesting. I'm a space geek, so I think that it's cool of how much that the heat transfer is so heavily dependent on the temperature of the object that we're talking about. So which temperature scale does not have negative values? The answer is Kelvin. I can tell you right now that your test will not have a question that easy, but it is just important to know that so that you can actually check if you get an erroneous answer. Water freezes at 32 degrees Fahrenheit. What temperature would this be on Celsius scale? Hopefully you know that 0 degrees Celsius is freezing point in Celsius. These are just, you should know freezing point of water in all three scales, and you should know the boiling point of water in all three scales. And if you know it in Celsius, you know it in Kelvin. You just have to add 273. So water boils at 100 degrees Celsius. What temperature would this be on the Fahrenheit scale? Once again, hopefully you know that water boils at 212 degrees Fahrenheit. Okay. Question 4. 3 objects, A, B, and C, initially have different temperatures such that TA is bigger than TB is bigger than TC. Objects A and B are separated by some insulating plate, but they are in contact with objects C through a conducting plate. And which of the following is going to be true when objects A and B reach thermal equilibrium with object C? So, as we said, the 0th law of thermodynamics, if A is equal to C and B is equal to C, that means that A and B have to be equal to each other. So that means that all three objects have the same temperature. Convection, only going to occur in liquids and gases, okay? So think fluids for convection. We'll never talk about convection of a solid. That's not a thing, okay? Two objects of different temperatures are separated by a wall. If the thickness of the wall is doubled, what happens to the rate of heat transfer? So if we remember our heat transfer equation, that is delta Q over the change in time, or just time, whatever, however you want to write it, is equal to conductivity times the area times the change in temperature divided by the length. So if I double the length, that means that I'm going to cut my rate of heat transfer in half. Okay. An iron bar with a length of 1 meter and radius of 10 centimeters, so automatically I know I need to change something here, is heated from the bottom by a lighter. If the bottom bar has a temperature of 35 degrees Celsius and the top bar has a temperature of 20 degrees Celsius, what is the rate of heat transfer through the bar? So I'm actually given in this problem the conductivity here in watts per meter degrees Celsius. And that's really important because that means that I need to keep these Celsius values in there rather than change this to Kelvin. Okay, so we're trying to find our rate of heat transfer. So we're trying to find delta Q over delta T. And we know that that is equal, as I said in the last slide, to Ka delta big T over L. So that is going to be equal to, this is just a bunch of math at this point, 80 watts per meter degrees Celsius times our area. We have a radius of 10 centimeters, so that's 0.1 meter. And it is a iron bar, so that means that its cross-sectional area is a circle. If we're looking at it like this, the collisions can only happen along a cross-sectional area. You are going to hear the words cross-sectional area more than you ever wanted to this year. I can tell you that right now, especially when we get into magnetism. So, and then our temperature change is 35 degrees Celsius minus 20 degrees Celsius, which is just 15, divided by the length, which I am given. When you do this out, you will get an answer of 37.69 watts. It should make sense that the rate of heat transfer is in watts because the rate of heat transfer is energy, and the rate at which energy changes, you should remember from AP1, is power. Okay. So, which of the following is responsible for raising the temperature of water in a pot placed on a stove? And select the two of the answers. So, vaporization, I did not say that that is a method of heat transfer, so that should not be one of your answers. Water is in contact with the pot, and the pot is what is being heated by conduction because the pot itself is in physical contact with the fire, so that means conduction is definitely at play here. And then that heat being transmitted to the rest of the water in the pot is done by convection. Okay, so the bubbles that are created as a result. So heating up the bottom layer, and once again, hotter liquid is going to be less dense, so those bubbles and that layer of liquid rise to the top, while the colder liquid that's currently on the top sinks to the bottom, and the cycle continues to go. So you may have heard before, like, it actually takes longer to boil hot water than if you just started out with cold water because it takes longer for the process of convection to actually start happening because there's less of a temperature difference with the hot water than the cold water and the flame. So that's kind of interesting. Once again, just a real life application of this. So hopefully this wasn't too boring. I know this was a super long lecture, so I am going to stop it now. We have 3 more to go.